and welcome everybody. I'm also excited to talk to you about the OSNAP program. I'm going to start by assuming that everybody has heard about the RAPID program. And many of you probably know that the RAPID program was the first trans-basin array that was put in place in 2004 to directly measure the overturning circulation. And just a little bit of history, that program was assembled because at the time, at the turn of this century, there was a concern that the overturning circulation was susceptible to a rapid change. And so the U.S. and U.K. community came together and put in that RAPID MOCA array, which is still operational. Now, shortly after that array was put in place, around 2007, a modeling paper came out, Bingham et al., which was the first that showed that instead of talking about the AMOC, the Atlantic Meridian overturning circulation, there really was more than one overturning circulation because it appeared as though the overturning circulation was gyre-specific. So from some models, and actually in an observational study that I conducted a couple years later, what was emerging was that the overturning circulation in the subtropical gyre was distinct from the overturning circulation in the subpolar gyre. Now, the controversy was, well, whether was that just on short timescales or was that on all long timescales or on all timescales? A few studies then came out that, a few modeling studies came out that suggested that the subtropical AMOC was principally wind-driven. Now, at this point, the U.S. AMOC program came online in 2007. An implementation panel was put together, and I co-chaired that with Kathy Kelly. And one of the first goals for that U.S. AMOC program was to put together an observing system for the overturning circulation in the subpolar North Atlantic. And so this sort of followed directly on the heels of, RAPID going in, but then also studies saying, well, actually, if we're interested in the overturning susceptibility to changes at high latitudes, then it probably would be a good idea for us to go up to the high latitudes and directly measure the overturning circulation there, where we can also measure the volumes of deep waters that are formed. So that was the motivation behind OSNAP. So I had to laugh a little bit when Victoria said this relatively new program, because it really had its origins. I started talking about it in 2007, and then in 2009 I held a workshop here at Duke, and at that point invited a lot of international colleagues who were interested in the North Atlantic. And so we ended up putting a proposal together. I'll talk more about those specifics later if you're interested in how the whole funding structure worked. But all of that is to say that we ended up getting 7 countries involved in this international collaboration. And the first OSNAP system, or the first deployment, was in the summer of 2014. So we were funded in the summer of 2012, and it just, took a little while to get everything together. But what you're looking at here is a schematic of it. Great. So the overall design is from Labrador to Greenland, then a separate line from Greenland over to the Scottish Shelf. We refer to that west line very creatively as OSNAP West, and the east line as OSNAP East. This design was put in place to take advantage. Well, one, we wanted to sort of have a separate accounting for the Labrador seawaters and then for the overflow waters, but also we wanted to take advantage of the Germans' array at 53 North, which has been there for 21 years. This line also goes through the OOI array in the Irminger Sea and coincides with the AR7 West, AR7 East hydrographic survey. So I'll get a little bit more into the design, but let me just tell you what the overall goals of the program are, and these are for the whole international program. So now I'm hoping that this moves forward. Kristen. There we go. There we go. It's just a really long delay. Okay, you should see something called OSNAP objectives.
Yes, we're good.
Okay, so the main objective is to quantify the meridional overturning circulation in the subpolar North Atlantic, and the meridional heat transport and meridional fresh transport. We also, as part of this program, Amy Bauer and I have a RAFOS float program where we are directly observing the pathways of the overflow waters. So this is the first comprehensive float program looking at those pathways in the subpolar North Atlantic. A real interest here in the measuring is to understand how AMOC variability is related to deep water mass formation. So many of you may be aware that in the recent IPCC report, there in this 21st century, the projected slowdown of the AMOC is anywhere, I think it's from like 19 to 34%. And the cause of that slowdown, according to IPCC and the climate models they use for their projections, the cause of that is a diminishment of deep water formation in the North Atlantic. Now, at the same time, we don't have any observational evidence that there is a strong connection between deep water mass formation and the overturning circulation. So in addition to monitoring, to measuring the overturning circulation here, a major goal of ours is to understand exactly what is that connection between local water mass formation and this larger scale overturning. We're also very interested in understanding how the subpolar and subtropical AMOC are related or are not related, on what timescales. And then finally, we want to understand what kind of configuration can we have for OSNAP in order to have a long-term, cost-effective monitoring system. So if you're interested, I wrote all up about the whole OSNAP program in a recent BAMS article. That's not the results, that's just about the design, the international collaboration, the goals, etc. So this is showing our OSNAP line on a background of the mean dynamic height, so you can see the nice anticyclonic subtropical circulation there, and you can see that OSNAP cuts across the cyclonic subpolar gyre. And I'm placing the OSNAP line in red there, showing you where it is relative to the AR7 West line that is occupied annually by the Canadians. There is the OVID line that is occupied every other year by the French. The extended Ellet line is run through by the British. And the 59.5 north is a hydrographic survey that the Russians occupy every summer. And then, of course, there's the rapid line. So here is a little more detail about our design. So unlike rapid, we have a number of basins to cross in the subpolar North Atlantic. So it's a little more complicated system. So we have 53 moorings, as you can see there, 33 ADCPs, lots of current meters and microcats and thermistors. So you'll see all the country contributions there. I'm not going to go through all of them, but we have Canadian, German, U.S. The U.S. OOI is there in the Erminger Basin. The Dutch contribute, UK, and France. China's contribution is joint with the U.S. in a glider survey not across all of OSNAP East, but across a portion of it where the North Atlantic current runs through. So that is showing you in a little more detail where we have instruments, and this is telling you where we are in terms of our data recovery. So we're looking here from July of 2014, when most things were put in, until our first recovery period, which ended in May of 2016. Everything that you see here was redeployed in the summer of 2016. And actually right now, for this summer, we have 5 OSNAP cruises going out and recovering data and redeploying. So that is ongoing right now. But this map shows you all of the different arrays, also shows you the gliders, and just telling you over what time period do we have data. So we have an overlapping 21 months of data, and we call that our phase 1. And I'm just going to show you some early results from that phase 1. So let's see. This is the showing you in plan view, OSNAP East is in the top panel and OSNAP West is in the bottom panel. And so wherever you see that red or pink shading, we have direct measurements of our velocity fields. Wherever you see blue, we are getting geostrophic velocities, and we're referencing them either with deep moorings or with surface velocities using altimetric measurements. There's the hash line showing the glider survey, and you can also see there are a few places that we have that are unmeasured, and we are filling at the moment with climatology. All the details of this, the methodology, is in a Lee et al., that's Lee, Lozier, and John's article that was produced, and there we ran a lot of Aussie simulations to see to what degree this design, in a model, these could capture the full AMOC and MHT and MFT. So here we're taking another look at OSNAP across both OSNAP West and OSNAP East. This is the mean salinity from our phase 1 from August 2014 to May 2016. And I will note that the timing of OSNAP was quite fortuitous because the winter 2014 and the winter of 2015 and 2016 produced really large volumes of both Labrador seawater, both in the Labrador Sea and in the Erminger Sea. And it produced convection to depths that haven't been seen since the mid-90s. So we are quite excited to have that type of convection, right after we put everything in place. So this is mean salinity, and again, what you're just getting an idea of is the array. So I will mention here that in addition to many top to bottom moorings, you can see where we're also measuring. We have short moorings that are really focused on the overflow waters. So for instance, on both the east and western side of the Reykjanes Ridge, we're interested in the Iceland-Scotland overflow water. And then on the western side of Greenland, eastern side of Greenland, you can see all those short moorings, and there we're tracking the Denmark Strait overflow water as it comes into that Erminger Sea. So these are our first results from that 21-month phase, and these are results we're just finishing a manuscript up on now, and I presented these at Ocean Sciences. And I know this isn't a call that is focused on the results, but I just wanted to give you a quick look at what we have found. So what you're seeing here in black is our measure of the overturning circulation in density coordinates for the whole array, and then in blue is across west, and in red is across east. You're also seeing that in the dashed lines the Ekman transport, and you can just see it's very small there, so I'm just going to focus on the MOC here. Ekman is almost negligible, especially across OSNAP West. So one of the two surprising things here that have come out of this, one is that the MOC across the subpolar gyre appears to be as variable as it is across the subtropical gyre. There's a range of about from 7 spherodrops to 24 spherodrops, I think, in the full array. And the thin gray line is the 10-day, is daily estimates with a 10-day filter. But the solid lines are 30-day estimates, and those are the uncertainty estimates in the shaded envelopes. So we are surprised to see this amount of variability. There's no hint yet of any seasonality, but I should probably have my PhD taken away if it was a 21-month record. If I would be figuring out a seasonal record here. Also, no evidence of any trend, but again, we didn't expect to see one. But the second surprising thing, other than the strong month-to-month variability, is the very strong contribution of OSNAP East compared to OSNAP West. And so I will remind you that many, many past modeling studies over the past decade or two have focused on the dominance of Labrador seawater variability to the overturning. And you may be familiar with many studies that have looked at the influence of the Labrador seawater, downstream in the subtropical basin. And so what's quite surprising to us is that despite two winters of very strong Labrador seawater convection, it appears as though from this record that our overturning is really dominated in the eastern part of the basin rather than in the western part of the basin, which means it implicates the overflow waters, or at least it implicates that the transition is taking place north of the OSNAP east line. The other thing that's very interesting to us in the MHT and the MFT, you're looking at the across the whole array in black, and you can see the uncertainty associated with that. And what we've done is we've taken the MHT and the MFT and we've looked at what fraction of that can be attributed to the overturning and what fraction of that can be contributed to the isopycnal component, meaning the flow that is moving along the same isopycnal. So by that we mean it's not involved in the overturning, because the overturning by definition means diapycnal. And what you can see is that for the meridional heat transport, the overturning circulation is really dominating the meridional heat transport. So, and this, in the freshwater transport, the overturning is largely dominating, but not to the same degree. So we're not sure that we would get this because we expected the gyre component, the isopycnal component, to perhaps be stronger. For those of you who don't think about the overturning circulation all the time, in OSNAP, the MHT and MFT are almost completely, the overturning is almost completely responsible for the MHT and the MFT, but we're finding something not quite the same, but we're finding that the overturning dynamics are playing a large role in the MHT and the MFT. This is a really first look at the OSNAP floats. So these are all the floats that have surfaced to date since as of June 2018. So our first deployments were in 2014. So everywhere where you see green is where floats were launched, and everywhere where you see red is where the floats surfaced. So you can see quite a bit of difference between the distribution of the green and the distribution of the red, and then the blue are the trajectories. So one thing that has been surprising, many of you may be familiar with the sort of the general view of the deep overflow waters in the subpolar North Atlantic is that they are so the general view has been that they're topographically constrained. So the overflow waters come down in terms of the ice and Scotland overflow waters. They come down that eastern flank of the Reykjanes Ridge. They go through the Gibbs Fracture Zone, and they would circle through the Erminger Basin and then through the Labrador Basin. And so what we are finding is that the waters that come through the Gibbs Fracture Zone are not going back up into the Erminger Basin, that they appear to be spreading westward and southward, and that goes along with a recent modeling studies that a graduate student of mine did. So we're still in the process of refining the tracking here, but there's the ice and Scotland overflow waters appear to not be going around sort of this traditional route where we would expect to see them, going through the Labrador Sea. On the other hand, the Denmark Strait overflow waters do tend to follow the more traditional western boundary current paradigm. So they're rounding Greenland, coming around the rim of the Labrador, and seem to be exiting the Labrador Basin. So this is a quick summary then of our first look. We have 21 months in hand. We see strong variability in the MOC in the subpolar North Atlantic. I've told you that the OSNAP East appears to dominate both in terms of magnitude and variability. The heat and freshwater transport seem to be largely controlled by overturning dynamics. Talked to you about the RAFOS floats. The observing system remains operational. All countries are still involved and committed to its continuance. And we have lots of next steps that I'm happy to talk to you about next. You can also find out more about our program at our website and again in that BAMS article. So hopefully that has given you enough of an overview of the OSNAP program. I'm happy to answer any questions.